Hi, I'm Dan Heidinga. I'm one of the project leads on the Eclipse OpenJ9 project, and I work for IBM on, I'm one of the leads for their core interpreter or core runtime team. It's my contact info, both Twitter and on GitHub, reachable just about anywhere. But what are we going to talk about today? We're going to talk about cloud native Java, and particularly cloud native Java with OpenJ9. So this slide is my important disclaimer slide. It says I work for a company with a lot of lawyers, and so don't take the things I'm going to tell you today and make product decisions based on them. All right, so what are the things I'm going to tell you today? Well, we're going to take a look at the economics of the cloud and how that matters to Java. Then we're going to take a look at Java on the cloud with OpenJ9. We'll run through a demo, and then we'll wrap up. Sorry, bear with me. I'm losing my voice a little bit. All right. So the economics of the cloud with Java. How many of you are actually using the cloud today? So I see some hands going up. How many people are using Docker? All right. So a lot of this applies whether you're running on somebody's cloud or even running locally. But if we look at the cloud, the number one predictor for cost is how much memory you're going to be using. Typically you get charged based on some kind of tiering model, so many vCPUs, and often that comes with a certain amount of memory. It's much easier to overcommit on CPU than it is on memory. It's much easier to get caught if you've overcommitted on memory because applications start to swap. And so this is really the driver for what your cost is in the cloud. It's how much memory you're using and how long you're using it. So the myth that has been prevalent for a long time is that machines have lots of RAM. It doesn't matter how much memory you take, there's lots of memory there, just go use it. So there's no point in optimizing for footprint. And this is somewhat true when you own the machines. When it's your machines in your data center, you can specify how much RAM is going to be in that machine, and you want whatever you're running on that machine to use all of the RAM. So this myth it's only a myth as we move into the world of cloud. The reality, though, is that footprint is going to drive more and more of our design decisions and more of how we write software. As a cloud user, you're paying for the footprint that you use, and as a cloud provider, you care about how many applications you can squeeze together. The more memory they use, the more machines you need to buy, or the more memory you need to buy to be able to get the performance that you're promising your users. Now, you might not think you're a cloud provider, but if you're running multiple Docker images on the same machine, you have a lot of the same constraints that a cloud provider does. If you're running many versions of Java on the same machine, a lot of the optimizations that cloud providers are going to care about actually apply to you as well. So as we look at the trends in the industry, we see movements towards virtualization. You have this big machine in your data center, you've chopped it up into smaller machines so that you can pack more things running on it. And we see a trend toward microservices. You've taken your big monolith, you've split it up into smaller pieces so you can scale them independently. But this leads actually to an increase in memory usage, because now each of those microservices is running its own copy of the JVM. So whereas before you had one JVM with a fixed overhead and your application took everything above that, now you're running N JVMs with that same fixed overhead. So I should clarify what I'm talking about when I talk about footprint here. And there's sort of three different things. The first is, how big is your image? This is the virtual CPU, or sorry, the virtual machine image. This is the Docker image that you're using. And this matters to your copy costs. It matters to how much storage it takes to store this thing, but that often matters for your cloud provider. But it matters to you when you scale. The bigger your image is, the longer it takes to copy it, the slower your scaling is going to be. We can also talk about virtual memory footprint. This is mainly a concern for 32-bit applications because they're limited to 4 gigabits. So we'll mostly ignore that as we're seeing fewer and fewer 32-bit apps these days. But the one we're going to mostly concentrate on is the physical amount of memory. This is the RSS. This is the one you're going to be charged for in the cloud. This is the real application cost. So what are the things that you can do to control that? We've all probably heard variations on this kind of topic that your dripping water faucet is going to cost you a lot of money over the course of a year. The same is true of your application. You probably have debug data that you generate all the time but rarely use. You probably have logging frameworks that generate all kinds of extra things, and these might be creating objects at runtime that are forcing you to use larger heaps than you'd otherwise have to use. There may be other parts of your application that by switching them out, you could be making big savings to stop those small costs and small memory increases. So what does this mean for cloud Java developers? Well, the simplest thing to do often to increase your performance is to give your JVM more memory. You give it more memory, you're going to spend less time GCing. But now there's a direct comparison between the amount of memory you gave your application and the amount of money you're going to be spending. Businesses like those kinds of knobs because they can tune them. And so you may find that when you say, I want to increase the memory of this, your business is going to say no. It's going to increase costs too much. Particularly if you used to fit in a smaller tier and this change is going to push you from being, say, a 128 meg application to needing the next size up, which might be all the way up at 512. So the net effect is you're going to be tuning your application, and you're probably going to be tuning it to fit into particular tiers, right? You're often not charged purely on the actual amount of memory you use. You're charged on the tiers or the tier basis. And so when you're going to make changes that trip you from one tier to the next, it's going to cost more. It's also going to drive our behavior as developers because we're going to need to know where our memory is being used. It means we may be picking components based on their footprint and not based on how easy it was to use or some other familiarity with it. You're going to be looking at how do I tune my app to fit smaller and smaller and smaller, especially as you look at scaling microservices. If you've increased the footprint and you only have a monolith and you're paying for one copy of it, that's one copy, it's not so bad. But as you look at your microservices, they're often split up so that you can scale them independently. An increase in footprint is often not one increase in footprint, it's really n times for everything you've scaled. So it really will be driving application behavior. Okay, so now that we understand that footprint becomes king, where does OpenJ9 fit into this? For those that don't know, OpenJ9 is a JVM, which means it's basically the core engine of Java. So you take your typical JDK, and if you've downloaded from OpenJDK, that JDK has Hotspot as the engine. So what our project does is we remove Hotspot and we replace that with OpenJ9. And the reason for doing this we'll get into throughout the rest of this talk, but it gives you a new JDK, OpenJDK with OpenJ9. And this JDK's got a long history. IBM's been using it in its products going back into the 90s for thousands of products. So it's a well-tested, well-tuned, well-built JVM. And I always like to highlight the license here. It's EPL v2 with a secondary licenses clause, which allows us to combine it with GPL class path. So that's why we're able to combine it with OpenJDK. So if you want to get a binary of OpenJ9, the place to get it is from the Adopt OpenJDK community. Has anybody heard of Adopt? Okay, I see a few hands, that's great. So Adopt is created by the London Java community. They looked at OpenJDK and said, it's really hard to build and test JDKs. And nobody competes on their build farm, at least not in the JVM space. So why don't we build one central location to build, test JDKs, to make sure that they're production ready, and make it easy for anybody to go get one. and to get one that's not just, hey, I grabbed some random tarball of the source, but it's ones with all the security patches applied. And then they've been nicely enough to work with us as a project to host our binaries there as well. And you can also pull Docker images from there, so, which I'll be using later in my demo. Why do I think OpenJ9 is good in the cloud? Well, it goes back to OpenJ9's heritage, where it started life as an ME VM. And a lot of the evolutionary pressures that drove ME are very similar to the pressures that are driving cloud today. So what did ME care about? What mattered for ME? Well, small footprint. You really needed something very small to be able to run on a cell phone. There's only so much RAM, there's only so much disk. But the one thing there usually is a little bit more of is ROM. And so if you're able to take pieces of your VM or take pieces and burn them into ROM, you could save on what you could use of that RAM because you weren't wasting it. Now it mattered too that you had very fast startup. If you had some Java game on your ME phone, you didn't want to wait 30 seconds for that game to start, you wanted to be playing it now. And not only fast startup, but you also wanted that game to ramp up very quickly. You didn't want it to get faster and faster as you played because, oh, suddenly the VM had jittered enough to warm things up. So these requirements, keep them in mind as we look at the next slide, which shows the cloud requirements. It's again, small footprint. Density matters for your cloud providers. Cost matters for the applications you're deploying. It's fast startup, right? As you scale out your application, you want your JVM to start as quickly as possible. And you want that immediate ramp up. You want to be able to get up to peak performance as quickly as you can because you're paying based on the time that you use. So OpenJ9 has something called the shared classes cache. These are the command line options that you use to enable it. The top option here, XShareClasses, enables, and the second one is a tuning option to tell you what size to use. So this says use a 50 meg cache because it's a pretty reasonable size for most applications. So what do we put in that cache? I've given other talks on class files and some more detail on how this works, but I'll just touch on it very lightly here. The class file format, how many of you have actually looked at the class file format? Oh, good, yeah. It's a horrible format, right? As a VM, it's a horrible format to work with because it's all variable sized. And so we looked at that and said, we really want to be able to, going back to our ME days, we really want to be able to put this in ROM, and we want to be able to make it very easy for the runtime to navigate that data and to deal with the variability. So we reorganized the class file and we created something we call a ROM class. Now a ROM class has all the necessary information from a class file. It throws out the pieces that are in there that are duplicated and you don't really need. But we also made it truly ROM. Back in our ME days, you could burn it into a ROM, and once it's been created, it's never written again. The other thing it is it's position independent, so you can move it around in memory and it doesn't matter where it sits as long as you know where it starts. Now, that's great for all the symbolic data, but a VM also needs to know about live values, right? Once it's resolved some methods, once it's looked up some fields, it needs somewhere to store those offsets. And so we have a RAM class, which is basically a cache for all those live values. All right, so that's a long explanation to get to this slide, which says, look, I'm running multiple JVMs. If I'm scaling, I'm likely running the same application or very similar applications. And so each VM is loading the same classes. Everybody has a copy of object. Everybody has a copy of string. Why are you paying for n copies of this, right? It's the same thing. So we looked at that and said, how do we take these ROM classes and save on that? So why not put them in a shared memory area? So this allows you to have one copy of that ROM class and let all the JVMs that are connected to that shared classes cache reuse that. And so if you're running your desktop, you have Eclipse running, and you've got multiple Eclipses going, they can share that same that same cache and start up faster and save on your footprint. Docker images, if you're running multiple Docker images, you can mount that cache in a volume, and so again, you get that same kind of savings. And this matters because why pay multiple times for memory that's identical? Now, VM hackers tend to be lazy people, and so once we have an area that lets us put some data away, we say, okay, cool, what else can I store in there to make my life easier? And the next thing we said was, it'd be really cool if we could store some of our JITted code in that same cache. So we call this dynamic AOT, or dynamic ahead of time compiled code. So when the JVM starts up, it's saved away its ROM classes in this cache. It's able to share them across VMs. It really wants to be able to share the JITted code as well. So rather than having each JVM compile the same code over and over and over again, we compile it once and we save it away in this cache so that the next VM, when it wants to start up, can take that copy of the code and start up quicker with that. So we typically see a 10 to 30% performance improvement using our dynamic AOT story. Now what this does though is it means that there are two kinds of runs. The first run has a cold cache, there's nothing in it. So as it starts up, it has to populate that cache both with ROM classes and save that JITted code away. And then runs after that start to warm up because you're running more times, they're able to reuse the things that have been saved. Now we typically only save the JITted code from the early phases of startup because it's less specific, it's a little bit more generalized, so it's able to be shared. Other code from the hotter compilations has become very specific to your application and may not be as easy to share. So this code, we can't run it in place. We actually have to copy it in, but that copy cost is trivial compared to the cost of actually compiling it. It's hundreds of times faster. So you get a very nice speed up out of this. And then for code that matters, we'll recompile it to make it even faster. So a couple of other tuning options with OpenJ9 is -X Quick Start. This is for applications that you want to get up and running very quickly. You're doing a bit of a trade-off here between your max throughput and how fast you start, but this will give you, very good startup performance. And then we also have Xtune Virtualized, which is for virtualized environments, so containers, for example. And this gets you that same kind of very fast startup, uses a lot of our AOT code, but it also enables idle management. So when the VM detects that it's gone idle, it'll run an extra garbage collection cycle to try to force down the amount of memory that it uses so it can give back the other memory to the OS. This is really important in applications where you're running a lot of things on the same machine or a lot of containers on the same host, because that way you can give back the memory you're not using and it's available for something else to be using it. So what does this actually look like? All right, so I have a demo. I'm just gonna, all right, so, so I'm not sure, is that readable? Should I make it a little bigger? All right, so that's my Docker file. Basically, it's pulling an OpenJ9 VM from the Adopt project's Docker hub, and then it's building Spring's Pet Clinic and just running it. Now, the reason I'm running Spring Pet Clinic is because it's a really nice little application that gives you a timestamp once it's started, so you can make comparisons between different VMs. All right, so I'm going to run that now. Docker run. So we see Pet Clinic starting. And we see that it started in about 8.6 seconds. All right, so then if I go over to my
Sorry, just finding my mouse back. So if I go over here, I'm going to start OpenJDK as well.
And we're going to see the exact same application run with OpenJDK. The only difference between these two Docker files is which base image they're using. And so here we see Pet Clinic started in 9.3 seconds. I'm running multiple things on my machine, but we see that the numbers between the two of them are very similar out of the box startup time. The important thing in this particular example, though, is if we go over here, I'm going to run Docker stats. And I'll make that bigger as well. And so what we see is one of these VMs uses 448 meg, and the other is using about 160 meg. So if you're taking your microservice and you're scaling it around, which do you want to be paying for? 440 meg or 160 meg? One of these actually starts to be micro and the other isn't. So the 160 meg, of course, is the OpenJ9. So there's one other thing I want to show. And so the other thing I want to show is with shared classes cache, Docker run, EclipseCon, OpenJ9 cold. And so what I'm running here is the exact same thing I ran the first time, but this case, what I'm using is my OpenJ9 with shared classes cache. I've enabled the shared classes cache feature, and we see that startup is actually a little bit slower. This is my cold run. So I've created the cache, but there's nothing in it yet. So I'm going to save this. Where's my mouse? So Docker PS, Docker commit. And I will call this my warm image. All right, and so now I will go back over here and I will run the warm image. Maybe I'll just run it from here. Docker run -it EclipseCon. And so this is the one I just committed, which has the warm cache in it now. And so we'll see how fast that starts. And so now it's down to 6.9 seconds. So we went from 8 or 9 seconds down to 6 or 7, right? So you've taken a significant fraction out of the warm-up or out of the startup of that Pet Clinic application. So what this gives us, though, is OpenJ9 with 2 tuning options gets you a much faster startup, and OpenJ9 with no tuning options is a significantly smaller footprint. So I'm going to switch back to slideshow. Okay, so what have we talked about? Well, just to put it in nice charts, because it always makes it a little easier to look at, is that OpenJ9 is about 30% faster startup when you're running with X shared classes and X quick start. So out of the box, the two of them start up basically the same amount of time. You enable the options and you're getting a faster startup. The footprint is about 60% smaller with OpenJ9. That's out of the box, right? That's no tuning, no nothing. You've got significant footprint savings. And this makes a big difference, right, in our cost in cloud. Now, this one I didn't demo, but it basically shows that OpenJ9 has 55% fewer wake-ups. This data was gathered with a tool called PowerTop. And basically what it does is it checks how often does your VM wake up. How often is your application paging itself back in and doing things? How often is it stealing CPU that it doesn't need? So why do you care about idle applications? Well, research has shown that most applications are idle a large portion of the time, or most servers at least. And so you want something that when it detects that it's gone idle, doesn't wake up, doesn't steal CPU from other things that are running. I have a chart, and it's not in this particular deck, but I mentioned the X2 virtualized earlier. And X2 virtualized enables the OpenJ9 idle detection. And so in that case, when the VM realizes that it's gone idle, it's able to run the GC to force the heap to contract, and then it's able to give memory back to the operating system. And I've got a chart, I wish I had it in this deck, that shows the footprint drop at these particular points where you're idle. And then this is a chart that shows the X2 virtualized and the AOT, showing that trade-off between that very fast initial ramp up and some of your peak performance. So the red line on this chart shows hotspot. This is hotspot out of the box, running with OpenJDK, running on a Java 9 VM. That was what I had current when I was running this particular experiment. And it takes a while to get up to speed, but it hits about the same max throughput as OpenJ9. So OpenJDK with OpenJ9 is that blue line. It takes a bit of time to ramp up, and then it gets to its max throughput, still significantly earlier than hotspot does. But what's interesting is that green line. For applications that are short-lived, maybe you're doing serverless computing and you really want something that comes up very fast. Maybe you're doing command line tools. You want something like that X2 virtualized, which gets you ramped up very quickly and gets you to its peak performance and then stays there. Yes, you're taking a throughput trade-off to get there, but if you're only going to live, if your application only runs until about here, you've actually won in most cases by using that option. So for short-lived things where you need to scale up quickly, do something, and then shut down, that's the kind of options and tuning that you need. So where does that bring us? Well, we started by talking about cloud economics and talking about the way that you're going to be billed for the memory that you use. And that's going to drive changes in the way that we code our applications. It's going to drive changes in the way we manage our applications, the way we think about writing code. Right? Suddenly, when you want to increase the footprint of your application, you're going to have to talk not only to other developers, but you may have to talk to your business about, is this improvement worth the cost that's going to bring to the business? Those financial metrics are going to drive our behavior, whether we like that or not. And so it's time to start now before you're in that position where you really want to add some feature and you can't because it's going to blow your budget, to start looking at how do you decrease the cost of your application? How, when you're looking at those microservices trends, how do you make it efficient to run them, efficient to run your Java applications in the cloud, efficient to run them on your local machines? And I think for a lot of things, the answer is OpenJ9. So I've got a couple of links here for the Adopt OpenJDK project that show you, where to download the different JDK versions, links to the GitHub project, to our project Slack. What we'd really love to do is to have everybody in this room go out, download OpenJ9, give it a try, see how it works for your applications and your use cases. Let us know, and we expect that there'll be a lot of positive stories, but like with any software, there'll probably be some roadblocks and some obstacles along the way, and we'd love to hear those too. So that's sort of my call for action is go out, check this out. It's open source, completely open source. Check it out, build it, run it, and let us know how it's been going. So Thank you. Yep.
Can I combine share classes with custom VM image? So with since Java 9, I can use JLink to create a custom image. So let's say that I want to keep only Java base, create my own image, and also use share classes.
Yes. Yep. We've tested shared classes with Java 9. It's module compliant, and all JLink is doing is stripping down your VM. It's giving you the same VM but with fewer modules, so it's entirely supported. Yeah.
What are the supported operating systems?
So OpenJ9 currently runs on x86 Linux, on Power Linux, on Z Linux. It runs on Windows 32 and 64, at least for Java 8. We're working on a Mac port right now, and we're working on an ARM port as well. So
Java had issue with running inside containers for quite some time, since Java 9 and Java 8 update, whatever. You cannot specify an option to be aware about the container memory limits.
Yeah.
Is Java OpenJ9 aware about this container memory limits?
So the question was about the new container awareness options that have come in OpenJDK, and we've added similar options. I think we've added exactly the same ones for a number of them: the enable container awareness and the setting the max RAM amount that your heap will use, setting it with percentages instead of the default XMX options. One of the really cool things about OpenJ9 is we have a single source base. So we're supporting JDK 8, JDK 9, 10, and 11 out of one VM source base. So we make improvements for container support. You get them in Java 8. When we added the new Epsilon NoGC that's showing up in, I believe it'll be in JDK 11, you'll be able to use that in JDK 8 with OpenJ9 because it's one VM code base.
Do you intend to follow the same release cadence as OpenJDK?
Yes.
2 feature release per year.
So, as I said, we're one source base supporting 8, 9, 10, and all the releases. So what we've been looking at is JDK 8 has quarterly releases. So we're going to try to track that and support the feature releases 9, 10, 11 at the same time. So the 8 release will come out, the next 8 release with all the security updates, and we'll aim to have 11, I guess, show up at the same time in September. We haven't been able to follow exactly with Oracle yet. We're still getting set up as the project externally, and so there's been a little bit of lag, but our aim is to catch up and be on that same 6-month cadence. All right, thank you, everybody.